Just a little bit of outline. I'm going to explain the motivation for CRDTs. I'll tell you a little bit about the basic mechanisms of distributed systems. And then I'll focus on conflict-free replicated data types. What are they? How do they work? How do you make sure that they are correct? And I'll show you a couple of examples, interesting examples. And then I'll talk about composing CRDTs and the kind of invariants you can enforce. I'll tell you a little bit about work in progress, of course, if I have time for all this. Okay, so motivation. What is consistency and what are the different degrees of consistency? So we talk about strong and weak and either weak or eventual consistency. It's about more or less the same thing. There's not a continuous spectrum between the two, but I'll try to make it simple. Give you a little historical perspective and also wonder why bother with all this. So the current motivation is about georeplication. So let's say you have a bunch of users. You recognize this kind of slide. I'm sure you've seen it 100 times before. You have a bunch of users who are interacting with some distributed system, some Facebook or whatever. And these people are reading data, but they're also executing code, or they're requesting code to be executed, and which will make changes to a database. So here we have 3 data centers, some geographically separated across the world, and usually users will interact with the closest data center because that gives them faster interaction. And you see that at each one of the data centers, we have some code running, and we also have a database, a copy of the shared database, right? The whole point of this thing is that people will be able to share their data, their information. So the problem here is that even the latencies here may be okay in the order of tens of seconds, but the latencies between the data centers are often of the order of 100, 200, 500 milliseconds. So you cannot centralize everything, also for reasons of scale. There are too many users. You cannot centralize everything, also for reasons of fault tolerance and availability. If something goes wrong in the network, you want to be able to redirect the user to a closer data center or a different data center, for instance. So this is why we do georeplication. But of course, and there's another reason also, is more and more of these applications are actually running on the mobile computer itself. So this mobile computer may be completely disconnected from the network, in which case the latency goes to infinity. So, and in order to continue to interact, that is to maintain availability, you need to have again a replica of the data and of the application on the mobile computer. So the problem is, how do you make, if this guy makes an update, how does this update become visible to that guy over there or to this guy over here who may be disconnected at the minute when the update happens? So usually you start little. You start with a single data center. You have a company in Paris with a database of its employees, and you can do updates to this database. I'm making employee Nelly purple, whatever that means, blue, sorry. Then I'm adding a new employee Bob, and well, someday my company becomes richer, and now I want to open a branch in California. So here I do this replication thing. I make a copy of the database in California. And now I want to do exactly the same thing, right? So I want to, say, add new user Bob in California. The problem is that if you want the two databases, the two replicas of the database, to be exactly equal, that means that every time you do an update on one side, you have to synchronize with the other side, right? And you're not allowed to return to the user's making this call to add Bob, but you cannot return this call from this call until you finish the synchronization. Okay, and I just told you that there's 100 or 200 or 500 milliseconds round trip between these two. So update on the California side, update on the Paris side. Every time you have to synchronize, you have to wait 500 milliseconds or whatever it is. So whereas when you had your single database, you had lots of processing power and parallelism, et cetera, and maybe you could run tens of thousands of transactions a second. Now you're down to 2 transactions a second or 10 transactions a second. Right? So all your expensive hardware is being completely wasted. So this is the reason why people are looking at a different approach. Why don't we just do it differently? That is, when I want to make an update here in Paris, I just do the update locally, return to the client, and propagate in the background, whatever time it takes. So this means that even if the network, so in the previous case, if the network is down, everybody's stuck, right? Because there's no way to synchronize. Here, even if the network is down, I can synchronize. So I can make my updates. So my database is always available. And furthermore, it's a lot faster because I never have to wait. Okay, so that I put in a lot more parallelism, and I can use my hardware completely. But of course, that raises another question. What happens now, since I'm not synchronizing? I could have 2 concurrent updates to Nelly, right? In California, they're trying to make Nelly red. In Paris, they're trying to make Nelly blue. And when I try to propagate, I'll see, hopefully, I will realize, or my system will realize, that there's a problem. What would be really nice is that if there was some magic that could combine the 2 updates, right? So I'm going to propagate, and blue and red becomes purple, right? Now, it's easy to put in a slide, but how do you do this in a program? How can you ensure that it always works? I mean, clearly there's some magic here underneath. And, well, you'd like to have some kind of guarantees that this is all going to work. So this is what the talk is about. How do you guarantee that eventually first of all, that your operations are going to be mergeable in the first place, and that it's going to converge. So this is called different things, usually eventual consistency. Little bit of historical perspective. There are different approaches. There's different reasons why people want eventual consistency. And there's basically 2 classes. One is because you're doing some kind of cooperative work, right? So you're used to using SVN or Git or whatever, which is one form of eventual consistency. You disconnect from your friends. You want to be able to make your updates to your local copy of your code independently of other people without being bothered by them, right? So you do your updates, take your time, and when you're ready, you propagate and you merge, okay? Now, there's a human in the loop here, right? The time it takes is very slow, and the human is very tolerant of anomalies and is willing to fix things by hands if it doesn't work out. So there's a lot of work on eventual consistency that is along this line, but this is very different from the line I just described earlier, where you have concurrent updates happening to databases at a very high rate, and of course you want the merge to happen automatically with no human intervention. So you have sort of different takes on this, and I will concentrate on this one today. If there are any questions, just ask. Right. And so the sort of the crux of the problem, or one of the most obvious cruxes of the problem, is how do you merge these concurrent updates? And you can see from this history that it's taken a very long time for people to understand the problem. So if you don't understand it, don't worry, you're in very good company. Right? So the first paper on last writer wins is 1976. CRDTs is 2011. And of course, there are lots of people who tried different things in the way. A lot of it is ad hoc. Some of it has principles behind it, but unfortunately, these principles are not always correct. So operational transformation, which is very well known, most of the operational transformation algorithms out there have been proved to be incorrect. They will not converge. there's been lots of work in the 80s, 90s, et cetera, on file systems. Most of it is incorrect for a reason that I will show you in a while. The first person to actually understand, sort of put down the theory, is Baquero and Mura in 1999, but their paper went completely ignored. But they are now co-authors on the CRDT papers. So, since apparently this is all so complicated, why do we bother? Well, there's a very good reason why we bother. This is a performance slide. I'm not going to explain what it means, but it looks nice, right? But the important thing here is to compare. You have different experiments. So basically, we're running some workload of updates to a database, and using different underlying consistency models. And here we have. Let's look at this one, for instance. Here on the left, you have the strongest consistency model, and here on the right, you have some of the weakest ones, all implemented using the same code base, so they're comparable. And the absolute numbers don't really matter. What you have to see is that each point here represents some workload, throughput and latency. So at this point, you have throughput of whatever, maybe 500 transactions a second, and each transaction takes 150 milliseconds to terminate, right? And as you increase the load, your database saturates, and at some point it goes bad, right? But here's the difference between strict serializability, which is the strongest consistency model that guarantees that everything happens in a strict serial order consistent with real time, and this one here, which is but I'm looking for this one here. You can't see it. Oh, it's there. No? RC. There, RC, yes. So RC is a very, very, very weak consistency model. And, right. So you can see that at the sort of the knee of the curve, which is the interesting point, the latency is 3 times better for RC, and the throughput is 4.5 times better, right? So basically, with the same kind of hardware, you get 12 to 15 times better performance, right? So you can spend 12 to 15 times less buying data centers, right? So it makes a big difference. Okay, so I'm going to tell you a little bit about the basic mechanisms. So typically people use what's called read one, write all. Okay, so here, this graph, this animation is going to explain what this means. Very simple. It means that every time you read, you just read from your local copy. Since it's a replicated data, so you just read from your local copy. But every time you write, you have to update all the copies. And here's the difference between weak and strong consistency, right? So let's say you have this so a client, so this question marks just mean this is a query, and this just means it's an update. So in order to do some transaction, you query the state of the database, and you say, okay, now I want to make this change, this effect, right? And you propagate the effect to all the different replicas. Now, the difference between strong and weak consistency is that under strong consistency, you cannot return to the client until all, or at least the majority of these guys have answered. So you have to wait. It's slow. And in weak consistency, you can do that, and therefore you end up overlapping different updates. So now you see that this guy has received update U before update V, and this guy has received them in the opposite order. So of course, if you're not careful, the results here and here are going to be different. The important thing here is that you cannot talk about global state. There is no global state. Right? The best thing you can get that is the closest to global state is what happens when all the updates have been received. So there's no updates in flight. Right? And so that's a local state, and what you hope is that all these local states are going to be the same. That is, that it converged. But, you know, it's not going to come for free. So there's different ways of implementing replication. Basically, we distinguish state-based and or Datashipping from operation-based. So state-based, basically, as the name implies, means that every time you want to propagate your updates, you just simply send your state, the content of your memory, or some representation of the content of your memory. So here I have two concurrent updates, U and V, happening at two different replicas. They make their local change, right? And then you just send the whole state to the other guy, and the other guy merges in the state somehow. And from this state, he may take the merged state and send it to someone else, who will again merge it into his own local state. And if you do this, you know, often enough and randomly enough, eventually everybody will get everything, right? Which is what you wanted. But of course, the problem is how do you ensure convergence? I will come back to that in a minute. The other approach is called function shipping or operation-based. Here, what you ship is not the content of the data, it's the code for the change, or the change itself, the delta. So here I'm sending to the change U that happens first on the middle replica to the other two. And here so now this other operation X, which happens, will see the result of U, and therefore we say that U is visible to X, even though U happened on a different replica. And here we have a concurrent update V, and V does not see the result of U, right? It's not visible. So again, the question is how to ensure convergence. But before I get to how do we ensure convergence, I want to come back to this fact that X has seen the result of U. So you would, in most systems just ensure first in, first out delivery, or sometimes even less than that. Which means that sometimes X could be delivered before U to some places, and that's anomalous. And I'll show you what that means. So let's take a specific example here. We have three replicas of your social network application where you post photos, and Alice has a replica at home on her home computer, and she executes the operation that says, in the future, I don't want this directory of photos to be visible to my boss, Bob. And then she goes and she propagates that. And then she goes to her phone and posts a photo. But if things are sent just in FIFO order, that means that Bob, or Bob's computer, might receive the photo first before receiving the change to the permissions. And therefore, Bob will see the photo, even though he's not supposed to. Okay. So what happened here is that the system did not realize that there is a dependence between V and U, because that dependence is sort of indirect, transitive through Alice's replica, right? So this transitivity is tricky, and it's most systems do not actually implement that. So what you would like is what's called causal order delivery, in which, since V is dependent on U, then you want V to be delivered after U everywhere. Okay? So causal order delivery says that if you have two operations, U and V observes the effect of U, therefore V should be delivered everywhere after U. But if U and V are concurrent, then there is absolutely no single order, right? So causal order delivery is a bit tricky to understand, a bit tricky to implement, but you can implement it without doing synchronization, right? All you need to do is to have some kind of metadata attached to V that says V depends on you, right? And if U is delivered first, if V is delivered first, the system sees, oops, it depends on you, there's a gap, I need to wait, right? And you just wait until U arrives, and then you push V afterwards, right? So you just buffer V for a while. But that requires some mechanism and some metadata. And metadata has a cost. There's another piece of metadata which is simply the log of your updates, right? Which you need to keep this log of updates in order to be able to deliver your updates. And as long as there's somebody out there who hasn't received the update, you have to keep it, right? So you have to do some kind of garbage. You can do some kind of garbage collection only once you're sure that everybody has received your update. And that is also costly. Okay, so what is eventual consistency? You may have read definitions. There's a very well-known definition that says eventual consistency is when when all clients stop making updates, then all replicas have the same value, something like that. That's a really bad definition because clients never stop giving updates. And furthermore, just saying that all the replicas have to converge to the same state doesn't tell you what state that is going to be. It doesn't say whether it's a correct state. So I have what I think is a better definition. So the top here implies the earlier one. So correctness conditions in distributed systems usually have a safety part and a liveness part. So liveness means something has to happen, and safety means something good has to happen, or only good things can happen, sorry. So the liveness part is that if I deliver an update to some replica, then all the replicas have to eventually hear of it and apply it. And the safety part is that any two replicas that have received the same set of updates, even if there's more in flight, it doesn't matter. If they've received the same set of updates, then they should have the same state. And I don't care, I explicitly do not care about the ordering of those updates, and I don't care about anything else than the set of updates, right? Because that's the only way, if you depend on anything else than the set of updates, then basically it's non-deterministic. So this is eventual consistency, but there are other properties out there that you often want in addition to just eventual consistency. So first of all, you want to make sure that the state satisfies some kind of specification. And so I'll talk about the specification of CRDTs in a minute. So it would be, if you just say they all have to reach the same state, well, that's easy. Just make everything null and empty the database and everybody will have the same state. But that's not very satisfactory. So you want to have a specification of what the state changes should be. There are some systems that do this by doing some kind of tentative update and then rolling back, and then another tentative update and then rolling back. That's really bad. So you don't want that. You want it to be monotonic. And as I explained earlier, you don't want these anomalies, these message delivery anomalies. You want causal delivery. Okay, I'll skip this one, and I'll talk about CRDTs. So what are CRDTs? CRDTs is basically, so it's data that's replicated and which is updated without any synchronization. So just like I explained earlier. But the two sort of key ideas of CRDTs are, one, that a CRDT is a data type. And therefore you encapsulate all the complicated things inside the data type so that programmers can use it without thinking. But the second key idea is that you can ensure that your data will converge to a correct value by construction. And there are some very simple properties that ensure this, which we will look at now. So first, let's take a state-based CRDT. So here we send state, as I said. So here we have some update at the top replica, F, and G concurrently at the middle replica, and we send the state, and you merge, etc. And you merge just like I showed you before. Now, how do you ensure that this converges? Well, when you think about it, what you want is a few things. Let me bring up the next animation. So first of all, you never want to go backwards, right? So what that means is that there's somewhere in your data type, in the definition of your data type, there's some implicit order, right? Once I've done an update, I never want to go backwards. Therefore, each new update should dominate the previous one. So there's some kind of order implicit. I haven't told you, I told you that you just send state around and basically it's random. So you might receive the same state several times. You may receive, or you may receive different copies of different states that contain the same update. Therefore, you want that to be idempotent. And the thing is, you never know in which order the merge is going to happen, and therefore the merges have to be commutative, right? And also, a merge may contain multiple updates, and therefore the merge has to be associative. So if you look at math theory and something that has a partial order and an operation that is idempotent, commutative, and associative is called a semilattice. So the only property you need here for convergence is that your data type is a semilattice, and you also want this monotonicity property. So we call it the monotonic semilattice. So it's a semilattice where the merge operation is the least upper bound or join. So let me take an example. Let's consider a last writer wins register. So last writer wins is a last writer wins register is a data type where the register contains some value and there's an associated timestamp. Right? And when you merge two updates, you just compare the timestamp, and the one with the highest timestamp wins over the older one. Right? So it's just like if you consider a sequential execution, it's just like a normal register. But when you have concurrent updates, the one with the highest timestamp wins over the other one. So how does this work? Here we have a write of some, so initially we have value A with timestamp 0. And now at the first replica, replica 1, we're going to write value B. And the time is 1. And we're also going to add the replica ID in order to distinguish concurrent times, concurrent updates. So it's B with timestamp 1.1. Okay, yeah?
Does this require that the different, say, data centers agree on time? Or is that
No, this is logical time. Lamport clock, it's logical time. You just keep a local counter. Every time you do an update, you increase your local timer. Okay, or every time you send a message. But of course, real time works as well. Right. As long as you have the two parts, your local time plus the ID, so that you can distinguish concurrent updates. Okay. So here we have the B timestamp 1.1, and here we have another concurrent update timestamp. It happened at the same time, so the timestamp is the same 1, but the second part is different, 2. All right, anyway, third one here. And when you merge them, well, timestamp 1.1 loses over, timestamp 1.2 wins over timestamp 1.1. And therefore, the final value here is going to be C. Yeah? Okay. And same thing here. D with timestamp 1.3 is going to win, and therefore it will converge. So I'm going much, much too slow. But if there are questions, go ahead. So we'll skip all the animations and go straight to operation-based CRDT. So as I said, operation-based, the operations can arrive in different orders. So the final state here, if I've received F first, the final state will be G of F of the initial state. And the final state here will be f of g of s, right? So if you want to be sure to converge, all you need is that operations g and f commute. Okay. And I will skip the last writer win example. But the truth is that most data types that you're interested in do not naturally commute. So how do you make this converge anyway? Well, you just have to define away the non-commutativity. So, and have some way of resolving concurrent operations. So here's an interesting data type, the set. The sequential specification of the set says that whatever the initial state, if I add E, then E is in the set. Whatever the initial state, if I remove E, E is not in the set anymore. There are no duplicates. Okay. Most operation pairs commute. You can do the exercise. It's easy. Add E with remove F. Add F with remove E. Add with add, etc. All this works. Okay. So I don't need to worry about them. But there's one pair that does not commute. Right? If I say add E followed by remove E, it's completely different from saying remove E followed by add E. Right? So now if I want to have concurrent add E with remove E, I have to do something. What do I do? Well, there are different approaches. You could say, well, let's try to synchronize, right? So that we all agree on which one is gonna come first. But of course, that's going to cost you synchronization. We're trying to get rid of that. So let's forget that, which is a perfectly good solution if it's fine for you. But right now, we're going to forget that. And so there are other approaches. The only thing you need to do is to make sure that the result is going to be deterministic, right? It only depends on the set of operations. So if the set of operations is add E, remove E, I need to have some deterministic outcome. And that could be, well, I might have a timestamp and say the one with the highest timestamp wins, or I could say concurrent add and remove of E is an error, and let's put some error indicator in the set. Or I can say I always want the add to win, or I want the remove to win, or I always want my boss to win, or whatever, right? As long as it's deterministic, you're okay. Deterministic, independent of order of delivery, independent of local state, and of course you don't want any synchronization. So, for instance, add wins seems like a cool thing to have. So let's see, how can you implement add wins? So this is what we call the OR set, means observe remove set. So I'm going to have to go pretty quickly through the animations. So basically, the behavior is what's down there. So let's say at the beginning my set is empty, and I add element A at the top. So what I'm going to do, the key thing here is I'm going to distinguish elements by the replica where they have been added or removed. Okay, so even though it's a set and there's only one A, okay, even if it was added 27 times, I will still distinguish internally in my concrete implementation this A as being a blue A. It's coming from the top replica. And concurrently, the middle replica inserts a brown A. Right? So when we propagate the state, this is state-based, if you propagate the state from the middle replica to the bottom replica and merge, you take the union of the local states and you have brown A. And then you propagate the blue one, and now the state at the bottom replica is both brown and blue A, but of course there's only one A, it's a set. Now if I remove A, well, what A could I remove at the top replica? The only one I can observe is the blue one. Therefore, I cannot remove the brown one. Okay, that's why it's called observed remove sets. So now I will add a deleted marker, what's called a tombstone, to my element A. And again, if I propagate and merge, now the final state is brown A inserted and blue A has been removed. So A is in the set, right? Because it's this one doesn't exist. And you can see that indeed we have a concurrent remove and add, and the add wins because we still have the brown A. So it works. It does what it has. So the semantics here is that So the sequential semantics is the same. All the commutative pairs remain the same. But this one, which is not commutative, you just decide, that's my decision. Whatever the initial state, when I have a concurrent add and remove, I decide E is in the set. That's why it's called add wins, and it's called OR set because you only remove the instances that you observe. Now, you can see there's something not very nice here, is that I have to keep this tombstone around. So can I get rid of this tombstone? Indeed, I can. If I have causal delivery, then I can take advantage of that. So here I'm not going to have tombstones at all. When I say remove A, at the top replica, you just take A out of your representation. And when you propagate, you're going to propagate this empty set. And when it gets here, this guy's going to say, well, I saw a blue A that was inserted. And now blue tells me there's no A, right? And because of causal ordering, I know that it cannot be swapped, right? So if I saw blue A and now there's no A, it means that A has been removed. And I can take it out. So I don't actually need the tombstone. I want to tell you about another very cool data type, which we didn't invent. It's called the replicated growable array, RGA. It's not well known, but it's very cool. Basically, it represents a linked list of elements. So it's something you might use for concurrent editing, for instance. And each element has a value, so I or n here, and a timestamp. And just like before, timestamp has a time part and a local replica ID. So here's my initial state of my linked list. So beginning and end guards, and then two elements in the middle. And now I'm going to insert a new element to the right of n. Okay. So I just update the linked list. So you remember this is replicated, huh? So this can happen, these inserts and removes can happen anywhere. And now I'm going to insert something else to the right of n. And so this insert happened on replica 2, and this insert now is happening on replica 3. And just notice that replica 3 is going to insert two things after n. So first it inserts I, right? So I comes after n, and now it inserts something else after n, which is r. And therefore it comes first, right? Because they were both inserted after n. And you notice that the timestamps are, when this happens, the timestamps are ordered in the opposite order, right? So the higher timestamp is to the left. So we're going to use that fact to resolve concurrent updates in the same way. So now if I have an insert, let's say at the beginning, I have two concurrent inserts at the beginning with timestamp 40.3 and 40.2, right? Well, I will resolve them in the same way, and I'll say, well, the higher timestamp goes to the left. And this is the result. So it's a very simple construction that allows you to maintain a sequence of elements. And it's very useful. So we have many CRDT designs. And you can use these different designs you can compose them to build bigger programs. So registers, last writer wins, different kinds of sets. Once you have sets, you can do maps. Then we also have counters and graphs, which are just compositions of sets, and sequence, such as RGA that I just showed you. But I want to show you some problems that you have with CRDTs. So what happens when you compose CRDTs? So let's say we want to, come on. Right. Let's say you want to compose, you want to create a file system, for instance. So you have a file system tree, you have directories. Each directory is a map. Map is almost the same thing as a set. You can use OR set to create your map. And each file could be some kind of CRDT data type. So let's say you have a sequence, and therefore in each file you can do concurrent edits because you're using RGA, for instance. Okay. So as long as you're just looking at individual files or directories, everything seems fine, right? You just have to apply the semantics of CRDT directories or CRDT files. But it doesn't work that way, right? A file system is more than just individual files or directories. There's also this tree relation between them. So what happens, for instance, if you delete something, let's say I delete A, while at the same time I'm inserting something under A. You have to come up with some reasonable answer for that. It seems that most people in file systems, in this case, if you delete a directory and insert something underneath, or edit something underneath, they will recreate the directory. Fine. But there's a harder problem. What happens if you try to move? Okay, so let's say here I want to move directory A under D on the top replica, and on the bottom replica I'm going to move D under A. Right. So I can't do that in sequential code, because in sequential code there's a precondition to move that says you cannot move under yourself. Right? But here you're not moving under yourself because it's all happening concurrently. So I could move A under D, and I can move D under A, and when I try to merge, whoops, I get something that's not a tree. And there are millions of distributed file systems out there that have this error. So what happened? What happened? Well, as I told you, there's a precondition to move that says you're not allowed to move in a sequential code. You're not allowed to move something under itself, right? What happened? Right. And so neither of these replicas moved under itself, right? But because the other replica was doing something at the same time, it ended up moving under itself. So what happened is that there's a sequential precondition that is violated by a concurrent update, right? And that's the typical case, and that's sort of the general case of invariant violation. So that's something you have to worry about. So I will, since I'm out of time, go straight to my Easter egg for you guys. If I can bring up my slides. Hello? So let's say we're composing some CRDTs and we want to maintain some invariant, some generic invariant. It doesn't matter what it is. Okay. And so I have a specification of my system where every update is specified in a sequential way. So it has a precondition. And the precondition is necessary to maintain the invariant. So if I just if I just run the code sequentially, so I assume that every operation has has a precondition. If the invariant is true initially, and the precondition of the operation is true initially, then the invariant has to be true after U. So I mean, this is typical sequential code, sequential composition. If each individual operation maintains the invariant, then any sequential composition maintains the invariant. But I need to check that, of course. I can, if I have the specification, I can run this in a proof tool and prove that this is true. Okay. But I also want to make sure that my precondition is stable, that is not violated by a concurrent update. So, first part of proving this invariant is doing the sequential proof. So, invariant is true initially. I run U, and I want to be sure that the invariant is true afterwards. So that's my proof obligation. And if that's true on this first replica, well, it's also true on the top replica, right? So since I proved it on the first one generically, I can assume it now on all the other ones. what happens now if I have a concurrent update? So as I said, I want to make sure, so this means concurrent, right? So if I allow these two updates to be concurrent, then I must be sure that the precondition of one is not invalidated by the second one, right? So I need to prove that after running v, the invariant of u is still correct, right? And if that's true, just by applying the other one, well, after applying u, the invariant is also correct, right? So if I can prove this proof rule, so what's really neat here is that I don't have to look at all possible combinations of updates. I only need to look at pairs, right? If for every pair the precondition is stable under that pair, then for any combination, it follows that the invariant is true. So we're actually applying this now, and we're sort of applying the rule backwards. So we say if we can prove this, then we're happy. Our invariant is true. If we can't prove it, we give this to a theorem prover, and if it's incorrect, theorem prover will give us a counterexample, and that tells us, well, here we have a problem with either our invariant is too strong or our precondition is too weak. Right, so we just need to strengthen our precondition, and strengthening the precondition might be, well, I'm not going to allow u and v to be concurrent, and therefore I have to put in some synchronization. So the upshot is, now you can take a completely concurrent system based on the CRDTs, combine the CRDTs, and infer the minimal amount of synchronization you need to prove, to maintain that one invariant that you care about. Right? So instead of the old way was, okay, if I have CRDTs, I have lots of concurrency, I can't maintain invariants like the tree invariant, so therefore I will use full sequential consistency, serializability, whatever, right? So you take this, one of these very, very strong models from your library of models. Here, it's the other way around. We start from something that is completely concurrent, right? And so therefore available, et cetera, and fast, and we add just, and if you need to maintain a specific invariant, we add just enough synchronization for that. Okay, I guess I'm really out of time, so I'll better stop here, and I hope there's a question or two. Yeah, 2, 3, 4, yeah.
You told that clients never really stop updating, but the safety rule you said is that if many clients receive the same updates, they will have the same state. In reality, I think that never happens too. So is that rule strong enough to express what things like CRDTs are able to achieve?
That's the best we can do. So we cannot stop clients from sending updates, but we can sort of isolate a subset of updates and have two imaginary replicas that receive just that subset of updates. And if those imaginary replicas are equal, then we're okay, right? And then we do this for any combination of updates, and therefore it'll converge. Yeah?
You set up this intriguing tree problem.
Yep.
Is the solution don't use trees, or is there a better solution?
There is no good solution. There is no good solution that does not use synchronization. So you can either accept that you lose the thing that is not part of, that has been disconnected from the tree. There's some systems that do that, many systems that do that actually without knowing it. So it's called a bug. You can sort of try to recreate these, replug these things back into directories, but the probability that you can get something that will actually converge by doing that is very low. Or you can introduce some synchronization. So move, the problem is not trees, the problem is move.
The synchronization will be on the latest update, or?
No, the synchronization is if you have one move that violates the precondition of the other move, then you're in trouble. So you have to check the preconditions So what are these, so if I'm doing a move within a left subtree and a different move within the right subtree, right, and they don't interfere, they're okay.
I had a second question. Could you show slide 65?
This is it.
That's slide 59.
Oh, I guess I changed the numbering. Huh. Yeah.
I was meaning to ask, so you say eventual consistency, or so you say eventual consistency is the only thing that you can really achieve in a distributed system without, I mean, getting bogged down by synchronization and all that. And we are preaching to, I mean, telling everybody the same message. So what the question I get back many times is from people who are used to strong consistency because they have been told by Oracle that that's what you get. They are used to a programming model that just wastes synchronization in a sense. Now, you've sketched an answer here that you might figure out the minimal amount of synchronization needed. But so is that a practical answer that we can give today, or is it still too early?
I would say it's work in progress. So we have the rule, we have the tool, we have proved a few of these things, and we have derived a few protocols. That's the best I can say. But it's obviously a lot more work, right? I mean, if your system gives you, you know, serializability or whatever, and that's good enough for you, by all means do that. I mean, eventual consistency is a lot harder. So it's only because you want 15 times better performance that you do this. Yep.
When you were talking about merging changes, for example, in the set example, you repeatedly referred to concurrent updates. How do you distinguish concurrent updates from non-concurrent updates? And aren't all updates in principle concurrent in such a system?
So I skipped tons of slides that would have answered that question.
Okay.
But, no, that's why causal ordering is important. So causal ordering tells you this thing depends on that thing. So if this thing depends on that thing, it has to come afterwards. And therefore, I don't care about concurrency, right? And I better apply, and if this thing comes after that thing, I better apply the sequential semantics, or else I'm going to confuse my users. Okay, so when things are causally ordered, by all means, apply the sequential semantics that users understand.
Thanks.
Okay, so
but that means your system has to give you causal ordering, and there are very few systems that give you causal ordering.
So we can do the last question if anyone has it.
Okay, so you said that on this slide, if you want to have two operations that can work concurrently, you have to, like for each pair of operations that you want to be able to have concurrently, prove that like the invariance and the precondition is stable. Thank you. Respected. What's like a sort of order of magnitude of the number of proofs you have to do there? I mean, is it like 1 or 2 or thousands, or does it really depend on what you're doing?
The hard work is writing down the specification, right? So writing down exactly what your precondition is, what your postcondition is, what your invariant is, that's hard work. And then once you give it to the proof engine, that's easy. Yeah. Okay. Takes a few seconds or whatever.
Thank you.
So we did a couple of, I mean, toy examples, right? But fairly complicated examples, and we can do the proofs in under a minute every time. Okay, thank you very much.